Hi, everybody. Welcome back to the Center for Health Informatics virtual speaker series. Today, we have Dr. John Osborne, an assistant professor at the University of Alabama, Birmingham. He started his work in viral and microbial bioinformatics and then transitioned and translational science while working on his PhD part-time. John finished his PhD at UAB in natural language processing in computer science in 2016 and now works as an assistant professor in the Department of Medicine at the Informatics Institute. His lab focuses on biomedical natural language processing, information extraction, and phenotyping. I'd like to give him the floor so we can start his presentation on finding clinical phenotypes of interest using natural language processing and transfer learning.
Thank you, Caitlin.
You're welcome.
Yeah, switch over here to presenter view.
Mm-hmm.
Okay, so like Caitlin said, I'm going to talk about finding clinical phenotypes of interest using NLP and transfer learning. And I'm going to start off by having a slide I pulled from a paper, and actually an ontology paper, but I like it because it's nice to have sort of a utopian goal of where you want to go with these types of problems when you're in the trenches. So this is sort of the idea of a learning health system. People have probably seen this before. The idea is, you go through these different steps. You start with your data collection, assemble it, clean it up, do your actual, knowledge representation application. And finally, take it back and, affect clinical practice. So that's kind of what we'd like to do at UAB here. When I talk today, I'm going to talk about three sort of things that relate to this. Three phenotypes actually of interest. One is reportable cancers, so kind of a reporting angle on what you can do with phenotyping. I'm going to talk about COPD flares as part of the clinical quality, and gout flares as part of a research program. So those are the sort of three, I guess, finding clinical phenotypes that we're going to be looking at. So this is sort of like the utopian vision of how it actually works, but in reality, it's a lot worse. So at least as the UAB. So you can maybe chime in later on about how it works in Calgary. But you have your clinical operations store, and typically some vendor has control of the operations store. At UAB, it's Cerner. Back when I worked for Northwestern, it was Epic. I know Meditech, I guess, is pretty big in Canada. And to get your phenotypes of interest, you typically do not hit this thing right here, because this has, live clinical stuff going on. And so you're going to hit some kind of data warehouse. And if you're like us, that's really hard to do. They make it basically you have to pay some money, and then voila, you can actually access your own data. I was told actually that's why we had to buy Cerner Power Insight, was to get our own data. And once you have that data warehouse, you need to figure out what's in there. Typically, they're pretty messy, and then use it for whatever your downstream tasks are going to be. So I've kind of outlined a few of them here that my lab's been working on. Some of the underlying stuff I'll talk about today if I have time to get to all of them. And then the idea is you can take that back and change your clinical practice for whatever that improvement is. Better finding reportable cancers. So maybe you're going to form public health policy, maybe change funding allocation and make trickle its way back to this. Could be for research problems. We're looking at, trying to find patients that have delirium at UAB, which is, and creating a data set of that, gout flares, and also for clinical quality improvement. So now where's transfer learning come in? So one of the things you would like to do ideally is be able to validate whatever you're doing at your own particular institution somewhere else. This article came out here. It's kind of snuck it in here at the bottom. This is in JAMA, just came out this week, looking at a sepsis validation tool that a vendor had sold. Pointing out that actually doesn't nearly work as well as prescribed. But it's really hard to do that if you can't share data sets, you can't share models, and you're handicapped by the inability to share data because of legitimate privacy concerns. So I'm going to talk about how transfer learning can help with that de-identification problem, and also how it's useful for information extraction. So it's kind of two areas that we'll be focusing on today. So I'm just going to go back little longer, back to 2009, for just a description of phenotyping, and just to point out that it's a very general problem and it doesn't have to necessarily involve even NLP. So this was for a blood bank. Basically, people want to look at give me all the patients that have autoimmune diseases. So that's your phenotyping challenge. So without the shared data sets, it's hard. Shared ontology, it's hard to do this. Back then, SNOMED CT was still pretty hard to get, and it still is if you're outside the United States. So we built this disease ontology that will let you basically take the UMLS disorder semantic group with all the cycles removed, convert it into OBO format, put some mappings into ICD-9, which was the the billing vocabulary of choice back then, and some other mappings as well. Do some manual editing, and we released that. So you can do your phenotyping this way just with billing codes. And when you have an ontology, you have some assistance with that. So you can actually see, there's a synonym here for autoimmune diseases, and you can kind of pull in a whole bunch of different things. So great, that helps, but billing codes aren't always that accurate, even though people are still using billing codes, to actually identify, patients. And for some diseases, it actually works pretty well. For others, not so much. But one of the other big thing about NLP that it really gives you isn't just the ability to find other stuff, is that you can really keep up to date with things. So this is work done a little bit earlier, about the same time actually, looking at some NLP results, just comparing GeneRiff. So GeneRiff is not actually clinical text; it's actually these little tiny snippets of text that you can attach to a gene in PubMed. And they're sort of like Twitter, I guess, for genes. And if you actually do NLP to look for these gene associations, and it's actually a nice sort of thing to look at because, there's actually a gene ID associated with it. So you get the gene right all the time. It's just a really matter of pulling, finding the disease in the GeneRiff. And you have much better recall looking at GeneRiff than you do for something like OMIM. You have a little better precision for OMIM. It's curated, but it just can't keep up to date. And that's a problem, not just with sort of these biomedical enrichment sets, but for any kind of phenotyping. I think we saw that very clearly, with COVID. There was no code for COVID, right away. A lot of even the phenotypes, weren't really well characterized, loss of smell, that kind of thing. So NLP gives you the ability not just to pull in new things, but to actually do it a little bit faster. Let's skip over that. Okay. So I'm going to talk about the first sort of phenotype of interest. This is from my paper back in 2016. And the problem here was to find reportable cancer cases. I'm pretty sure you have reportable cancer cases in Canada as well. We definitely do in the United States. Because I think NACER is actually the North American Association of Certified Cancer Registrars. So I assume that includes Canada as well. And the problem here is you want to find these so you can report them up to the state and federal level in the United States, probably provincial, I guess, in Canada. And, there's this huge, complicated, book, basically, that says how you're actually going to code this stuff, what counts as reportable and what doesn't. If there's like sort of a heuristic that I would use to describe it, I would say that, reportable cancers are the serious ones. But, you can't really code that up. So they have all this documentation for it. And what I want to show you and want to take home here is that you can have actually a pretty complicated phenotype, but still get a lot of value out of it. So at UAB, under the old system, the way they would actually find these reportable cancer cases was look basically at pathology reports. And this is like, I guess, 2014. They would actually print them out and look at them to find these reportable cancer cases. So not particularly a good way of doing it. And so what we did is we basically used MetaMap, which is maybe not the best choice anymore, but we're back a few years now, to do some concept normalization, to grab things that look like cancer, and then do some filtering, some rule application to filter things out, and then join that with the billing codes to do some machine learning, and then predict whether or not a particular medical record number has a reportable cancer or not. Okay. So how does this work? So this is actually, the way it works for the registrars is they actually log in So it's actually integrated now into our Cerner kind of website. During COVID, they needed to use external registrars and work remotely. And so it suddenly became really important. So they actually did the work of getting it integrated there as basically as a web application. So they click on this. This is sort of the top part of the web application. And they can't actually see the patients. They actually have to click the sort of get next button right here to get the patients. And the motivation for that is you don't want the CTRs to basically take all the easy cases. You want them to actually, take a random case so that, cases that are easy to abstract, they're not cherry picking those ones. And once they have that case, pulls up in a little website, they can see the different notes that are involved. For this application, they just see the diagnosis code as well, and the actual clinical document. We kind of highlight, what sort of, concepts that we think, may be reportable for them in the sort of right-hand side. They can click on those and go to the note. And I'll show you that note a little bit later. Once they have that, they can basically decide that, this is a valid cancer case and click the validate button. They can reject it. Or if it's a case that they've already looked at, going back on this slide here, you can get a validated case. They actually use a different tool, a commercial product, to basically abstract that case and report it. So we're really just helping with the finding component of it. And they can complete that case so it disappears from their list, basically, from the system. So that's the basic workflow. So here's some examples. It's MetaMap. So really it's a dictionary-based approach to normalization. There's no deep learning. It came out well before that. But it has a lot of rules, a lot of heuristics, and it's kind of like I would say it's a fairly common normalization comparison point, hundreds of citations. So it's, from that perspective, it's still good. It's not actively developed. I think there's a MetaMap Lite that some folks are working on that's supposed to take over, but it doesn't quite have all the features yet. Anyway, so it does a negation. We put some of our own rules to handle basic context type stuff, which we didn't have back then, looking at making sure that cancer was specific to that patient, not the family, or not in some donor. So some of those types of rules. So, we have this is sort of the error analysis that we have for it here, listing some false positives and false negatives. The sort of general trend was, two categorical errors. One is that institutional reporting rules. I don't know how they are in Canada, but in the United States, you can be diagnosed somewhere else, get treated somewhere else, get a second opinion. And so cancers are reportable specifically to an institution. So we didn't handle that at all in our code. So we would often maybe find a cancer that's reportable, but not reportable to UAB. So it wasn't actually any good to them. And the other problem we had is, concept granularity and specificity. Sometimes billing codes, may include reportable cancers and not reportable cancers. So when you're working with that, that's kind of what you're stuck with. And then, just other sort of NLP errors here. This is biopsy site is not melanoma. This is actually, I think, a reportable cancer here. Okay. So for predicting the patient's status, we tried a bunch of different machine learning. Again, 2016 published, so no deep learning or anything like that. We had basically, different features that we tried using. We have a very crude and simple one, which is whether or not they had some kind of, QE, a concept unique identifier, or concept from a pathology report, or they had a billing code, or they had both. So only 3 features. We tried just with the concept name, which is really the NLP bit, whether there's an ICD-9 code, and then merging them together for all the features together to do the prediction, which was the best overall if you look at F measure. The more important thing they cared about, though, was the faster rate of case completion, because that's really where this was funded by an internal UAB grant. So they're looking for kind of a return on investment. And it's hard to see from this graph right here, kind of the blue bit, but there was an improvement in the how fast it took them to do it. And in fact, they didn't want to go back to the old system at the end of it. So what I'm trying to say here is that you can, identify reportable cancers, even though, you have limited, granularity for your codes. You don't have any training data necessarily. We didn't have to create a whole corpus for that, which would have been really tough, especially with the sparsity in these types of codes. But the reason we could do it essentially is because you have this human machine cooperation. You have this interactive tool that humans actually get to verify and vet. So if you work together with them, you can actually solve a problem, which is pretty hard, as long as you keep humans in the loop and just accelerate it. So I want to give kind of an update sort of where it is right now, because, people publish papers and whatnot, and, sometimes it's just really there for the paper. So this system is actually still running today, which is kind of nice. I think there's about a dozen or so CTRs, and that improvement rate is still there. And it's been, great return on investment for UAB. And we have, added in external access, so people can work remotely from home, completely using this tool. So that worked out well. A few problems that we should have thought of maybe before or were in scope to do originally is it was a single disease system, really just looking at reportable cancers. Weirdly for me, even though I do NLP, we didn't think to put a comment box in there. So for people who ever do any kind of phenotyping, having the ability for the people who are looking at your predictions to actually write comments if they're maintaining it is really important. That would have solved a lot of problems. Also in the United States, we have this rapid quality reporting system now, which means they want, cancers to be kind of segregated by type. And, there's different quality metrics and, turnaround times you want for different types of cancers. It's a constantly evolving process that I'm not super familiar with, but you need to support, multiple types of cancer. We also ran into trouble after about 5 years with cancer recurrence, because after 5 years, you're considered a cancer survivor. And so it's a new cancer. So we didn't account for that very well. And also we have expectation creep. Now they're used to the system, they just want it to be improved. They don't have only a few of them are left that can remember the paper reports. So I'll talk about basically the system that's going to replace it next. A few other things, some bit rot over time. We moved to ICD-10 codes, but there's no funding for doing machine learning with ICD-10. So now we just, give them all the pathology report hits. It's actually not as big a problem as you think. And their desire for what they see has changed over time. They originally, when they were short-staffed, they were more focused on getting just the good cases. And now they're trying to get them all. Now they have more staffing for it. So the machine learning was actually minor. I would say the main thing is having the NLP for this particular system. And we haven't updated either the version of UMLS or the Ford's criteria as well. And there's no transfer learning here yet, but I'll get to that. So the replacement system, I published that in 2018. And it's basically sort of the multi-disease version of the Cancer Registry Control Panel. The idea is you can spin up a new registry, an interactive registry for folks with minimal or no coding by basically changing some configuration files. And we added some de-identification capability. That does use transfer learning in 2020. We haven't published that component yet, but I'll talk more about that at the end of my talk. So the original use case for this I'm going to talk about is for chronic obstructive pulmonary disease. So I gave you a good case of how I succeeded and how wonderful it is. And I'll tell you how I failed for the COPD case, just to give a little balance to the talk. So the goal here was to identify inpatients at UAB hospital for intervention. So looking at a bunch of different things, ICD-10 codes, DRGs, which you may not know, they're diagnosis reporting groups. They're relevant to Medicare and how you get paid. The idea is you want to know about them because you want to avoid readmissions. If UAB gets a readmission of a COPD patient, they don't get paid as much money. It's a big problem. They also want to use it for research. And so we did some NLP for them. That wasn't particularly interesting. I'm not going to talk too much about it. I'm going to focus more on the transfer learning stuff later. On the chief complaints and on the notes as well, we had separate sort of just regex criteria for the two of them. It wasn't a super difficult set of things they were looking for. And just to remind people who are not clinical or don't know, COPD is actually the third most common cause of death in the United States. You may have heard of bronchitis and emphysema. I think that's like COPD is like the new umbrella term for both of those diseases. And so you really, when you have these flares of COPD, it can really cause a lot of extra damage. So you want to prevent that if possible. So here's a screenshot from the feeders registry showing basically the configuration panel. You can see some of this. You can actually configure the tabs here. Some tabs, you can use across all registries, like the all registry patients tab. Some are specific, to COPD that you have to still do a little bit of development for. But otherwise, you can plug in, billing codes or DRG codes that you use to identify the different patients. You can also put attributes on the patients, like whether that COPD is really a COPD or maybe they're an asthma patient. And then we also can put attributes on encounters, because there's this notion of an anchor encounter. And then if you're remitted, within 90 days of this anchor encounter, then you have this trouble with billing. So here's what it looks like for the COPD registry with everything kind of blacked out, all the PHI hopefully. But they have these multiple tabs here. You can see the ones that they need to see today. These are these 8 particular patients. These are people in the 90-day window or in the Medicare 9-day window. They also had a relaxed criteria. If they, I guess, have more time, they can maybe, check out a few other patients, see if they have, should be visiting them. So it's this sort of list-based approach rather than the sort of button-based approach that you saw in the CRCP tool. And, the way we sort of checked out how well we're doing it is we took our patient population, what they were really interested in was whether they got people that got these 3 different DRG codes right here, 190, 191, 192, and compared how they would do with sort of the existing non-NLP kind of methodology, which was really scattershot. There's they were getting it from 6 different sources. They had some stuff from billing codes. They had referrals, census. They had a lot of different things that they were kind of trying to put it all together. And feeders was kind of nice because they got a consolidated sort of patient tab list of their patients. And for this 3-day time period, we got 43, they got 41. So not much of a difference, a little bit better, but it was certainly better, for time. They weren't spending so many hours per day on this, or so they were saying, versus the NLP. So should be great. Outcome today, not very good. So it hasn't actually been used since summer of 2019. The feeders tool itself is still being used, so that worked out, but the actual COPD is not. And the reason is, if you can do better than what the standard is, you really have to make sure that standard is actually a standard. So if you pay nurses to do some particular activity, they'll do that while the money's showing up during the development stage. But they're not really interested in logging into an application and finding these patients for research, or even to get the list of COPD patients that are inpatients. And the reason is they are so busy that half an hour a day is still a half an hour too much. So it's much easier for them to fit in these COPD visits sort of ad hoc. So I think the lesson for this, if you don't have dedicated personnel or dedicated time for this, you may be designing something that no one is actually interested in using. So I'm happy to take questions later about how to fix this. So we'll probably put the NLP on the pulmonary function test. We couldn't get that right away due to some problems getting documents from Cerner, but we can get those now. And my other approach I'm thinking is to kind of fix this problem is just to send out an email. So they really don't have to interact with the system at all. They just get a list of email of who the inpatients actually are, and they can visit them if they have time. But things are also kind of a little bit on hold, COVID-19, obviously, even after even though I can't blame the lack of use due to COVID-19, it certainly made trying to fix it harder because these are pulmonary nurses and they're obviously overwhelmed in Alabama during COVID. Okay, so I'm gonna jump ahead to the transfer learning bit. So for people who don't know, I assume people have a pretty high knowledge here. So I'm going to skip over this. I was told by Caitlin that most of you are pretty knowledgeable. So just for people who don't know, real quick, transfer learning, the idea is you have, instead of training, separate models for on several data sets and getting different models, you can actually take a particular source data set and pre-train on that and then use it to do other stuff. And so, here's, the Wikipedia calls it, inductive transfer or whatever. But typically now in NLP, we're talking about, some form of language model. I hesitate to use the word language model. People get upset, if you're a purist, the model doesn't actually give you a probabilistic prediction of the next word. They're like, it's not a language model. But all the language model, replacements basically that have come out since, really 2017, 2018, probably 2018 actually. Okay, so yeah, so you have your source data, which is some unlabeled corpus of notes in NLP, and then you can do a particular task that's going to hopefully be useful for whatever your downstream task is. The language model task, or a closed task where you're predicting some missing characters or words or subwords, or whether or not the next sentence follows it or not, like in BERT. And there are so many implementations now. I honestly find it hard just to kind of keep up with it. I'm listing a few of them here that are kind of more relevant for my talk, but there are a lot of different models out here. I can't cover transform model in this talk, but I will just briefly mention BERT. I know people talk about transfer learning in the context of phenotyping. They may be talking about patient transfer learning, which is a little bit newer, this kind of work. So I'm going to disappoint you if you're hoping to hear about hierarchical attention networks. I'm just going to talk about transfer learning in sort of the NLP context. And most of the stuff for this talk is sort of BERT and its derivatives based. So BERT made a huge impact. I basically had to redesign big chunks of my NLP course in 2019 because it really took the state of the art quite far, frustrating a lot of people. A lot of the work people had done, you could throw BERT at it and get a lot better result very quickly. BERT has this pre-training task. They do the masked language model task. They remove mask 15% of the text and try to predict that. They also have this next sentence prediction task as well. And hopefully after this pre-training, you're going to learn something about language that'll be useful for whatever your downstream task is. So for today, I'm going to mostly be talking about sort of name entity recognition as a downstream task, but it could be any number of other downstream tasks. So the one I'm going to jump to is a recent work from last year, trying to identify gout flares in chief complaint text. And so the motivation for this is that you really want to provide continuity of care after an ED visit for an acute flare. A lot of the folks that come to UAB emergency department, that may be the only contact they have with a physician. So if there's a chance to recruit them for a clinical trial, this is maybe a good place to reach them at. And because most of them are just discharged at home without follow-up care. So I'm also interested in this from an NLP point of view. Chief complaint text is really interesting, and I'll show you some examples of that down the road. There's not really good corpus for chief complaint text, so that was also good. And I also want to see what you could do with transfer learning on chief complaints. So this paper was published in 2020. This is in AMIA last year. Okay, so it is gout. So we're looking at gout and gout flares. About 9 million Americans, so maybe a little less than 1 million Canadians are affected probably. And they get opiates a lot, which is a problem for opiate use disorder. Older age, male sex, lower income, African-American race are all associated with these ED gout visits, which is all relevant for UAB. And a lot of comorbidities associated with them. It's not just like, I have some pain, there's a lot of other problems you can get with gout. Previously, people had really been looking at detecting gout with administrative claims data. And then Zhang in 2014 actually did some NLP to help with that, some keywords and spelling corrections. And he actually put into a machine learning algorithm and, could find gout cases retrospectively. But the problem that we're actually facing is we actually want to find these folks when they're being processed by the ED department, not like a month later or whatever. So The other issue is, we're, operating with our Cerner alerting environment, which you can't just roll. I don't know how it's in Calgary, but you can't just, get a transfer learning, model and deploy it really easily. But I was going to train one anyway, just to see kind of what was being lost. And for the billing codes, they're just too slow. I mean, it takes place days after the patient leaves the hospital. So that's not the data you really want to use. But chief complaints are kind of great. They've been used in biosurveillance a lot, as sort of early detection. They're created by charge nurses. They're really terse. Like here's an example of a chief complaint down here, heavily abbreviated text. Definitely different from what you normally see with a lot of the clinical corpus that come out there for NLP. So we had created 2 data sets on this sort of an initial gout enriched data set that only had the word gout in it. We actually couldn't find some of these older terms for gout at all. And gout is nice in that it's very specific. The only sort of error I found that we would hit it just from looking for the 4 characters together, gout was a typo. The problem with this corpus though from 2019, that it's obviously not representative of, ER chief complaints, right? Because it's all selected for gout. It's a little biased. So we just basically pulled a month from 2020 and got everything, which may or may not use gout or whatever else. So those are our 2 data sets. And we did this kind of interesting annotation process, probably because we're resource constrained in terms of chart review. Chart review is kind of a painful, expensive thing to do. We'll have a new paper coming out. We do a little bit more chart review and more results, but there's basically 2 labels we're assigning, sort of like the predicted label, which is if you're reading this, does it seem like this person may be having a gout flare? This would be sort of your predicted here. If like someone comes and says, I'm out of gout medicine, that's kind of suspicious that they're maybe having a gout flare. Whereas some of these other ones, may not actually have anything to do with it. This person may be having a heart attack, maybe had a previous history of gout, but wouldn't necessarily predict that just from reading it. So this is sort of like this chief complaint review, I guess you could call it. And then we actually did an actual review for some of these, but not all of the cases. There's just too many medical record numbers to go through, guided by the sort of GAFO criteria, whether or not it was a real gout flare or not. Okay, and we got pretty reasonable annotated agreement. I'm not going to spend too much time on that because I just realized we're at 137 here. And we created 3 algorithms. So we have sort of the super naive sort of baseline algorithm, which is if it has the word gout, then probably it's good to go. And then we have sort of like in my ideal world, if I could use transfer learning and BERT, what could we do? I can't actually deploy that in the health system. And then we had sort of like a simple model, which we actually ended up deploying, which is really looking for the word gout, but make sure it's to the left of a previous medical keyword. And then, or maybe if it's in the past medical history, that's okay if you have, one of these gout locations here. So case insensitive ones here and some abbreviations here. And this is our little gazette here for, past medical history. UAB is a little weird like that. We do actually have a mini past medical history in our chief complaint. Okay. So this method here, I just did vanilla BERT, nothing particularly exciting for it. I did try a couple other sort of BERT derivatives like BioBERT. I'm not going to talk too much about that. It's pretty standard. Let's talk about the results now. I think the most interesting part is to kind of focus on, I think the stuff in the box right here. So you can see the different algorithms on the 2020 corpus, which would be like a realistic, model of, what you're getting, since this is not, pre-selected to have the word gout in it. Obviously naive, gout flare, which always predicts gout. If it sees gout, it's going to have 100% recall on here because that's what this corpus is. But what's interesting here is you can see, the potential benefit you could get if you could actually deploy these kind of systems, right into, into actual clinical practice. I think there's definite value there. So, we couldn't actually deploy, the BERT Gout Flare algorithm, we can at least show that, there's some value to it. If you want to see code or more details on this, it's on GitHub for people that are interested. Okay. One of the other things that we did as part of this, which is something I'm trying to do all the time if I can, is we actually created the corpus for release. We put it on PhysioNet. I'm not sure if people are familiar with PhysioNet. It has a lot of biomedical data sets. They kind of maintain it. They have a really nice infrastructure for setting this up. You can click on here if you actually want to see the actual corpus. And you can actually go there if you sign the agreement. You're not going to try to identify these folks, though hopefully you shouldn't be able to do that anyway. You can go ahead and download the different chief complaints and use them if you want for your own purposes, whether it's gout flare identification or for something else. I'd be happy for folks to actually, try this or add it, as part of an additional fine-tuning process for language models. If you ever need to do any work in predicting something from chief complaints, because like I said, the text is very interesting. So we did this, based on sort of the FAIR principles, of and reproducibility in particular. That's why I wanted to do it, and also improve our own ability at UAB to do deidentification. And we've got deidentification integrated now with feeders, not through here so much, which is the patient list. This is just masking out people's names and giving them a fake, medical record number called DID and offsetting dates. But also for, basically, when you use a tool, you can actually demo a particular registry to someone and not worry about whether or not they should be seeing that text or not, because it's been de-identified. So here they can still see that, this patient has a lung cancer neoplasm. This is for like a little demo registry for a cancer registry, because we haven't moved the old CRCP tool to the new feeder system fully yet. But you can see this without actually seeing any PHI. Okay. So how do we do this? The corpus we took was how we do it. We basically pre-annotated the chief complaints using BERT. We also use another version, sort of a derivative, I guess, almost of BERT, another transform architecture called Albert, which I had some success with. It's similar to BERT, and this is transformer, but it has fewer parameters. They split, the vocabulary embedding matrix into like two smaller matrices, so they can really reduce the size of this context-independent matrix for the vocabulary and have increase as much as they want this context-dependent hidden layer matrix. And they share their parameters over layers. I don't know it's that much better than BERT. They perform actually pretty similarly from what we could tell for our data set. And then we had some regexes in here for stuff that, specific to UAB, interactions with the Birmingham Police Department in the ER, removing organizations like that. And so we took these models right here, and then we fine-tuned them on the I2B2 2014 data set, and then use that to pre-annotate basically our chief complaints. And this corpus, I'm going to go kind of quickly through here, is I think one of the better de-identification corpora. Long-term records on 301 patients. It was for coronary artery disease, but the de-identification is good for whatever you really want to use it with. So we use this as our for our fine-tuning, and they have pretty, I think, risk-averse annotation process on purpose. They go through two round proofreading and rounds of sanity checking. And I think that extra categories they put here are quite reasonable. They also included all ages for de-identification, not just those over the age of 89, which is okay under HIPAA, but you have to do a little bit of statistical work if you want to include those people. So we incorporated that as well, and made a couple other changes I'll talk about. Well, I just mentioned now is we also got rid of very specific time information as well. We found that sometimes you get very specific time information in these things, which could potentially, someone is wearing wearable device and that kind of thing. They might know who they are if they read that particular piece of text. And so we do our annotation after we pre-annotate. We have our annotators go ahead and do the the final annotation. And we've cooked this Sprat tool, which you can get online. Unfortunately, it's not being developed anymore. It does have a nice web interface. I may look to moving to something else a little later on, but it does support multiple tasks. It's very flexible. But also, I went through a lot of work to get it integrated into Citrix here. And so we're just going to keep using that for now. So these are some examples of chief complaints from UAB. They're actually in alphabetical order because they have actual little quotes here. So it's not a very representative sample. But, basically we would, the pre-annotation process is these things over here, either Albert or Bert is picking up or regex type system. And then the actual user just marking as being PHI if it really is actually is PHI. Okay. And then we did, sort of manual inspection. The IRB I have for, de-identifying data requires that there's a manual inspection process at the end. So I can't just get away with just, running some algorithm and shipping it out. I'm not sure I'd feel comfortable doing that anyway. So we had everything was inspected by human annotators, and they had pretty good annotated agreement. Some of these numbers were like, well, that's still pretty high, you're laying stuff out, but actual real de-identification is really much higher. If you miss like, some date somewhere or part of a date, it's not enough to identify that patient. So, real identification is actually much better than it's ever reported in most of these tasks. And the other thing we also did to make, just to add a sort of little extra security is use this tool we may call Brat Synthetic. This was a poster in AMIA this year. And what it does, it takes like a Brat annotation file and basically adds a bunch of fake data. And we really actually using this guy's library to do that. Faker does a lot of the heavy lifting. And it tries to give, synthetic text that looks a lot like the original text. And the idea is you want to have something for training, if you're going to use this as a language model that you could actually just plug in right away. Not a bunch of weird commented out, stuff in your text, which is going to mess up your training for your fine tuning for your model. So that's why we did this. And I mentioned we added that time thing in here as well. We still have some problems with it. Like we don't know if someone was injured in a restaurant, for example. We may change the profession, to being a carpenter instead of cook, but really the cook's the realistic one in there. Well, I guess a carpenter could be in a restaurant, I suppose. And also we don't have consistent PHI substitution. I'm not sure we want that necessarily, but the patient name can change throughout the note. But that may be better, especially if you're looking at a longitudinal note, because if you keep seeing a certain patient's name that was missed, say something that's very easy to miss, like a name like Young or White, or that has some other meaning in English, that kept popping up on the notes. People can maybe figure out that this was actually, Mr. White in the note. So we should probably put that as a parameter. Okay. So, so that's kind of published work. So now I'm going to show you stuff that I'm like kind of working on right now. So we're looking at de-identification at UAB. So the shared tasks typically you do for de-identification, they're really kind of artificial, I mean, if you're actually working at academic medical center, you already know what the guy's or girl's note is, right? It's what their name is, what their date of birth is, this kind of thing. So theoretically could use that information to improve, real world performance of your DID. So I'm trying to figure out, what is actually the best way to do that. So that's one of the things I'm struggling with right now. I'm also trying to figure out how important it is to have actually, local training data, which is kind of expensive to get versus integration with EHR. So we're looking at doing some experiments to see how that's going to work out. Do you have local document training? Yes or no? And are you integrated with the EHR? Okay. So we actually have a data set, and this is the work of DB, who was at UAB previously as a postdoc, and he helped put together this this whole data set. And we have another piece of software I don't have time to talk about today that he worked on. Focus more today on transfer learning, but it's a little bit different from the I2B data set we talked about. We use only binary categories, which makes it a little harder to re-identify it, or to add in surrogate data rather than having distinct elements. And he also removed all ages, all professions. So a little bit different from that, but fairly similar in the sense that you can use it for DID. So as a baseline system, we have NeuroNER implemented at UAB. I'm just going to put a quick word in for this system. I think it's a really great system. I think it was really state of the art, at least until 2020. So a couple new publications come out with people doing better things with de-identification. But this integrates really well. You can integrate with BRAT. You can use it to train your own data, bring your own data. And so we actually implemented this one first as part of feeders for our de-identification, and it's worked out really well. Here's some numbers when it came out. Beat obviously the old 2003 data set, came close to beating both these data sets, which is really good because there was no hyperparameter optimization or ensembles. And those are in some ways, if you spend a lot of time on a data set, you're going to increase performance a lot. But there's none of that with this. So it worked out pretty well, at least published model. We tried it on our own UAB data as well. We didn't have quite the same level of success. So this is just the NeuroNER results on our UAB data set. And looking in green here, that's all just with UAB data. That obviously works the best, if you actually have your own data. So that probably can't be understated. I was a little disappointed that you couldn't just take, the 2014 model and, apply it and get some better results. So that's I think a little disappointing from the transfer learning perspective. I think it may be due with how the annotation scheme from the UAB data and the 2014 data match up. We had to do a conversion process for the 2014 data to convert it to binary data. So there may be some issues here. This is obviously not published work yet. So there may be some work on that. And this, we kind of did a dumb way for doing it first. We tried combining the two different data sets as one merged data set, but we probably should have fine-tuned on one and then the other. And we started doing that, and I'll show you that on the next slide. So you can see that you get some benefit for applying some general rules, although it's very slight. You do get a little bit of better recall. Some of these general rules here are kind of UAB specific things, like UAB health system, for example, where the EHR specific rules are related to that patient. So adding in some patient specific information, which mostly actually didn't help very much. So with our system here, sort of our BERT-based system, we do get a little bit better results, but we haven't quite standardized everything here yet. One thing that jumps out there right away is if you have multiple sources of de-identified data, don't do what we did for these three ones here, where you try to merge into a set. It's actually much better if you, go through, additional rounds of, fine tuning, and you'll get a much better result. Okay, get some of this. Okay, so these are just some results on the 2014 data set. We got some pretty good results with BERT for the looking at this data, because no one really cares yet, at least since we published our data set, how well we did on UAB data. And we do a little better with the binary classifier. I don't know if it's part of the conversion process when we train on the multi-class, but it doesn't quite work as well. And yeah, so we're a little off the best report results from the 22-14 data by about 1%. We didn't quite replicate our results on the 2014 data with NeuroNER. I think there may be some, tokenization annotation discrepancies. And there's different ways to count agreement. You can do token-based or you can do entity-based. You get a little better if you have, you can count tokens rather than entities. So future directions, we'd like to resolve some of our evaluation framework here, and do some figure out better ways to combine the data sets and some better hyperparameter optimization. I was going to talk a little bit about a similar problem, but I'm going to go over this real quick. So I want to leave at least 5 minutes for questions. And I think I have like 2 minutes left here. So we did participate in the Cantimus 2020, even though no one in my lab actually speaks Spanish, but we were interested in cancer reporting. So we decided to do it anyway. So really briefly, we use sort of like these sort of systems. we always use regex just as sort of like a base, but the system is beta right here. This is basically like the Spanish version of BERT. And we had two different implementations of it. One is Flare, which is kind of I like it. It's a nice little toolkit. It uses Hugging Face as well. But you can just grab their off-the-shelf implementation. Then we did our own implementations in PyTorch using Hugging Face directly. One with beta, one with MBERT, which is like a multilingual BERT, to see how that worked out. The reason we did our own ones rather than just rolling off Flares, we wanted to kind of play around a little bit with adding in, extra knowledge into BERT, which is something we're struggling with. So these are just, working notes basically from these. So this is not like a, it was peer reviewed for this, but it's not a, the final system we hope to create. Skip over the regex, it's not that interesting. So we tried to basically use some of the heuristics we see in MetaMap to improve BERT, basically. So looking at things like, coverage, how well do we cover, this particular entity, cover a concept in sort of the dictionary term. So we had access to the Spanish dictionary for all these different cancer codes. And also cohesion, are these engrams in alignment, so this is just, our continuous set of engrams. We had a bunch of different features. Unfortunately, we just stuck with subword and character. I think if I would have done word, I would have had a lot better off. I don't really have time to explain these, but it was kind of a throwing the kitchen sink at it, looking at, different ways to measure what sort of how well the fit is between a particular set of subwords and the dictionary entry, its name or its synonym. And so what we really did is just basically add in this extra layer and then added in this sort of encoding. Maybe it's better to show you on here. So this sort of get subword coverage vector thing is this, crazy set of vector that we threw in there that would say, give you some information. I think it was, it changed in terms of how many elements we added to it, but it had like, the things from that dictionary list, and we just concat it with the logits and then do our classification basically. And we're still working on that. So some model parameters. I'm just going to skip over that. Results, which were pretty awful. It didn't work very well, sort of in short. We didn't see any benefit from our approach with that dictionary at all. And we were about 10 points. We submitted some wrong results, our older results, but even so, we're about 10 points behind the best system. So a ways to go yet. So I'm looking for ways to kind of improve that. So I'm just going to throw up the acknowledgement slide here and then maybe take some questions now because I know we're at 1:57.
For more information on who we are and what we offer, visit our website at coming.ucalgary.ca/CHI. If you are interested in our services, collaborating with our team, or have any other inquiries, contact us via email at chi@ucalgary.ca.